So now we're going to look at some applications of all of this stuff to differential equations. And I'm actually going to start with part B. And this one is verifying. So these are the directions that should be here. Verify that y is the solution of the differential equation. So remember, when we want to verify a solution, all we do is we make substitutions into the differential equation. So this is first order. We do have to take a derivative here. So if we were to take the derivative of this guy, so let's write out a few terms so we can actually see what that derivative is going to look like. So if n is 0, we're going to have negative 1 to the 0 plus x to the 0 times x to the 0. If n is 1, negative 1 to the first, x squared. N is 2, negative 1 squared, x to the fourth. If n is 3, negative 1 cubed, x to the sixth, and so on. So just to kind of reduce what's going on here, this is going to be a positive 1, so we do have a constant for that first term. Minus x squared plus x to the fourth minus x to the sixth. And then so on. So you can see what that pattern looks like. Now, if we were to take the derivative, we're going to have 0 minus 2x plus 4x cubed minus 6x to the fifth, and so on. So you can see how we're going to lose that first term because we have a constant there. So if we were to write this guy out, I'm actually going to go here. We would start at 1. That would be the easy way to do this. It's going to be an alternating series. We would bring that exponent down. We would subtract 1 from the exponent. Now, let's see if this matches what those terms would be. So, let's do a check. If n is equal to 1, we're going to have a negative 1 to the first times a 2 times x to the first. If n is 2, we're going to have a negative 1 squared times 4 times x to the 4 minus 1 is 3. So is that producing the same thing as what we know we should get here? And we can see that it is producing it. So we know this guy has to be correct. So it's always good to double check what you think that sum's going to look like. Now let's make our substitutions. So we have 1 plus x squared times y prime, and y prime is the sum from 1 to infinity of negative 1 to the n times 2n x to the 2n minus 1 plus 2x times y, and y was the sum starting at 0 and we want that to be equal to 0. So let's write some terms out and see what's going to happen. And remember, we're looking for patterns. So if we substitute a 1 in here, we're going to have a negative 1 to the first times 2 times 1, x to the first, If we substitute in a 2, we're going to have negative 1 squared times 4 times x to the third. If we substitute in a 3, negative 1 cubed times 2n x to the fifth. And then if we substitute in a 4, negative 1 to the fourth times 8 times x to the seventh. And then plus 2x times, now let's write this sum just a few terms out so we can see what's going to happen here. If we were substituting in a negative 1, substituting in a 0 into this, we would have negative 1 to the 0 times x to the 0 plus negative 1 to the first times x squared plus negative 1 squared times x to the fourth plus negative 1 cubed times x to the sixth. So let's clean this guy up a little bit. So we have that 1 plus x squared. And I'm going to clean up that first bracket. So that's going to be a negative 2x plus 4x cubed minus, this would be a 6 if we reduce that, 6x to the fifth plus 8x to the seventh. And then here, if we were to clean this up, we're going to have a 1 minus x squared plus x to the fourth minus x to the sixth. So we're going to do some distributing here. If I were to distribute that 1 to everything in here, and then if I were to distribute that x squared, and I'm going to line everything up vertically, so it's going to be a negative 2x cubed plus 4x to the fifth minus 6x to the seventh, and then so on. And then let's distribute that 2x in here. So we're going to have a positive 2x. And once again, I'm lining up vertically. So if we check out what's happening, notice those x's cancel, the x cubes cancel, the x to the fifth cancel, the x to the seventh cancel. So we can only assume that everything else is going to cancel also. So we end up getting 0 there, and that's what we wanted because we said that that differential equation in the beginning was equal to 0. So we have verified that this is true. So then now let's move on to, well, what if we want to solve a differential equation? So moving back to A, and I've changed the directions. This is what the directions should say. Find a power series solution of the form y equals the sum from 0 to infinity of Cn x of n, x to the n, of the differential equation y prime plus y is equal to 0. So our techniques that we've used throughout the course really come into play here. One of the techniques we used was we took derivatives and we substituted everything in, and then we solved it. So that's what we're going to do here. If we were to take the derivative of this guy, it would be the sum from 1 to infinity of n times Cn x to the n minus 1. So that's your power rule. The index is starting at 1 because the first term would be constant if we were to list this out. So then when we took the derivative of the constant, we would actually lose that term. So now let's make our substitutions. If we were to sub this and then our y into that differential equation, here's what we have. So there's our y prime. Here's our y. We want that to be equal to 0. Now, we really need to combine these power series. So let's change this guy. If we move this back 1 so that it starts at 0, then it will move this up 1, and this exponent will change to an n, which matches what we have here. The goal is always to try to factor out an x to the n, if you can. So that's going to replace all those n's with n plus 1. So they're going to have here n plus 1 minus 1, which will give us x to the n. So now we have that. And then now we can put these guys together into one power series. They both start at 0. They both have that x to the n. So then our coefficient would be n plus 1 times c of n plus 1 plus c of n if we were to factor out that x to the n. Now, this goes back to that identity property we talked about before. The only way that if I'm adding a whole bunch of numbers together and I'm going to get 0 is if this constant is equal to 0. So we're going to set that constant equal to 0. And let's solve that for c sub n plus 1. So if we were to subtract c sub n, and then we were to divide by n plus 1, then c of n plus 1 will be equal to this. That works as long as n is 0, 1, or 2, or so on. 0 because we started this sequence at 0 here. So now we're looking for patterns. So it almost becomes like a game for us. If n is 0, what is this going to look like? Well, if we were to plug 0 into this guy, and I'm going to box this in, then our C1 would be equal to negative C sub 0 over 1, which is negative C naught. Well, what if n is 1? What would that look like? If we plug a 1 in, we're going to get C2 is equal to negative C1 over 2. But we had a substitution for C1, so let's make that substitution. So we have negative 1/2 times C1, but we said C1 was equal to negative C sub 0. So we're going to get C0 over 2, or C naught over 2. Now let's look at when n is 2. So we're trying to figure out that pattern. What do those coefficients have to look like? So if we plug 2 back into this guy, we're getting our C3. C3 would be negative C2 over n plus 1, which will be 3. But we know what C2 looks like. We said C2 was C naught over 2. So we can write all these constants in terms of C sub 0 or C naught. So we have negative C naught over 3 times 2. And I am going to leave it as 3 times 2 in case we need a factorial here. And in this case, we probably will. So n is 3. Let's substitute 3 in. If we plug 3 in here, this is going to give us what C4 looks like. So we're going to have negative C3 over 4. And C3 Going back to that previous one was negative C naught over 3 times 2. So we're going to get a positive C naught over 4 times 3 times 2. So we can see the pattern coming up here. Our goal is to be able to express that. So if you remember in the beginning of the directions, said that our original solution is assumed to be of this form, and then we found a derivative of that, and then we plugged all that information into the differential equation. But now we have an idea of what these constants are going to look like. So let's do an expansion here. So if we were to expand that out, if we plug in 0, we're going to get c sub 0, x to the 0, which is 1. And then we would get c1 times x to the first, plus c2 x squared, plus c3 x to the third, plus so on, and so forth. Let's make those substitutions for our c1, our c2, or c3, and we'll go up to c4 since we found c4. So we make our substitution here for y. So our c sub 0, that one's pretty much going to stay the same. But c1, we said was negative c sub 0, negative c naught. We said c2 was c naught over 2. We said c3 was negative c naught over 3 times 2. And then we said c4 was c naught over 4 times 3 times 2. And then so on. So let's see if we can write this in terms of some kind of summation. Notice all of these have that c naught in common. That was our goal. So let's try to rewrite this guy. So we could think about this as an x to the 0 power. So we see an x to the n if we start at 0. We also see this alternating sequence. So let's try negative 1 to the n. That's going to give us a positive, then a negative, then a positive, then a negative. So now let's think about those denominators. We kind of see a factorial coming out here. So this is 4 factorial. This guy is 3 factorial. And then we have a 2 factorial here. We could do a 1 factorial here and a 0 factorial there. And that will give us our solution. So there's our power series solution. Now, it turns out that this guy is actually the series for e to the negative x. Okay, why is that true? Remember what e to the x looks like. E to the x is that. Then if we replace x with a negative x, could think about this as negative 1 times x to the n over n factorial. So then we would have negative 1 to the n, there's your alternating part, x to the n over n factorial. So there's your power series for e to the negative x. So there's our solution.